Okay, this module is on distribution. And the learning objectives for this module are discuss distribution facilities, primary feeders, transformer banks, customer services, etc. Compare overhead and underground distribution systems like Y and delta, single phase and three phase. Explain single phase and three phase transformer connections. Describe the differences between primary and secondary cables and hardware. Discuss residential 120-240 volt AC services and panels. Apply lessons learned about distribution, primary load to the power system simulator. Okay, this slide shows how distribution systems are generally radial feeders, which means power sources at one end only. You're going to see that when you have, the old days it was very strict this way. Radial feeders, that's all you had. Because if you wanted to trip a breaker, then everybody's out of power. Well, with smart grid and a few other innovations that are coming on, we're getting automatic transfer switches. We're getting, switching going on. We have distributed generation, so that we have multiple generators on systems. So times are changing. The main focus, though, is that with radial distribution, you can have circuit breakers or reclosers actually trip a line, re-energize a line, all from a single source. So radial versus looped. You might have in distribution a looped system, but there'll be an open switch somewhere, so the power is really going to an open switch and it stops, and then the other side of the switch might be powered from a different feeder, but by closing the switch you can parallel the feeders, you can transfer load by opening up other switches, what have you, and you can end up with using distribution to transfer load, but it operates in a normal condition radially fed. Okay? So that's the basics for radial feeders. Okay, now let's look at a feeder. This particular one is a overhead Y primary type. Now, we talked about the Y grounded three-phase systems. This is a distribution line. You can see the three phases up on the top of the pole on the right. You can see the three phases, three transformers, and the neutral just below the transformer. Right here is the neutral. Three phases and the neutral, three transformers. Now in a three-phase configuration where you have the three phases and the neutral, transformers are generally hooked up line to neutral. So on a 12.5 kV system, line to neutral is 7,200 volts. So it's 7,200 volts, giving you 120, 120, 240. Notice that the transformer producing 120 between those two bushings and 120 in those two, and 240 the whole range, is off of one phase. So it's single phase. Okay. Now if you have a fused lateral or lateral coming off going down a street with very little load on it, you might have one phase in the neutral, and usually they're up on the top like this so that you have a balanced weighting, loading, so you don't have an issue where over time the cross arm starts to sag, and yet this might be a phase conductor down years from now, where you put the neutral down here and you add another one up on top and reconfigure, and you got yourself a three-phase power line. So it's kind of built for a little bit of future. Now here's a delta, three-phase delta. Now notice in the actual drawing here, in the delta there is no neutral. No neutral, no ground connection there. All your transformers are connected phase to phase. If you're going to bring out a lateral, it's going to be two phases. Delta is three phases, no neutral. Advantages and disadvantages. Some of the disadvantages here is when a line falls down, it's sometimes hard to detect that there's a line on the ground. You have to do some special changes or equipment in the substation, referred to as zigzag transformers or grounding banks. And what they do is they try to improvise for a neutral connection in the ground to measure the imbalance on the delta to give you an idea of what's going on out in the field. If there's an extreme imbalance, then you end up tripping the breaker, doing that type of a protection scheme. But deltas, there used to be a lot of deltas, and the standard is to get rid of them is wherever possible, whenever possible, and not allow any more to go on to the systems all across the country. It used to be by saving that fourth conductor, it saved a lot of money. It's fine to run a three-phase pump out in the farmland somewhere. But when it gets to reality, because of delta transformer banks and what have you and grounding, there became a lot of stray currents and a lot of issues with voltage. So more and more these deltas are being changed out to grounded Y, and the standard is to have grounded Y distribution. But there's still delta out there, out in the mountains and places, or out in the real rural areas. You'll still see a lot of delta, but the standard is to not have delta. Okay, let's look at a single-phase transformer connection in a Y configuration. A couple things to note. You have two high-voltage bushings here. This is going to like the A phase, and then you have over here the neutral, so it's line to ground, which typically would be a 7,200-volt connection if it's a 12.5 kV system. If it were a 25 kV system, which is actually 24.9 phase to phase, phase to ground divided by the square root of 3 is 14.4 kV. So if you have a line to ground 14.4, that would be a Y system too. But on a 12.5, 7,200, the most common in the United States, you have 7,200 here, and you have two secondary coils. Okay? 60-to-1 turns ratio between these two coils and 60-to-1 between those two. So that gives us 120 volts across here, 120 volts across here, and 240 volts across the two extremes. So when you're looking at a transformer here, connected A phase to neutral, it's 120 to neutral, 120 to neutral, 240 from hot leg to hot leg. Okay, so that's a standard, typical connection. Now note, since this transformer bushing connects to the neutral, you don't need a bushing there. So a lot of utilities say, I'm going to ground that wire to the tank since I have to ground the tank anyway, and eliminate an extra bushing. And that is true. You're going to ground the tank anyway, so you don't need that bushing. You just connect it internally. So you might see single bushing transformers. If you do, that's because it's a line to ground system and a bushing was eliminated because it's connecting to ground anyway. Now, there's the single bushing transformer connecting to ground. Same idea. Okay, now when it comes to three-phase, it's a little different, and it's a little tricky. So, when it comes to three-phase, we have three transformers, and we're going to connect these transformers up in a grounded Y configuration. Actually, it'd be a Y-Y in a lot of cases, and it could be a delta on the high side, Y on the secondary. But by this jumper going across like this is showing me that it's a grounded Y connection. Okay? And here are the four conductors coming out, so it's going to be three phases and a ground. And we'll go through this. I want to show you how three-phase transformers are hooked up. Little bit of complexity here, but bear with me and we'll figure it out. Our standard transformer, if you recall, had two windings, and they were connecting up in series, so you'd have a hot leg, a neutral, and a hot leg, and you'd had 120, 120, 240. What we have to do for three-phase is go inside the transformer, take the lid off, get your hands full of oil, okay? Get inside there and reconfigure the jumpers. You take the A here and the C here and make that one connection point. The B and the D make it another connection point. Now, depending on which secondary bushings you use, you can use the two outside ones, You can use the 2 on the left, or you can use a 2 on the right, whatever your company standard is. That part doesn't matter. The part that matters is it's alley cat, bad dog. Okay? It's a common phrase, or other ones too. But alley cat means tie those two together, and bad dog, tie those together. When you do that, you basically have 120 volts in parallel. So, if I were to take 2 batteries, I have 2 batteries. Hand me 2 batteries, please, right over there, right behind the computer laptop. I want to demonstrate something here for the. Thank you. If I take 2 batteries, let's say they're 120 volts each. Okay, in our standard normal connection, we have it like this. We have them together. We have them in series. So it's 120, 120, 240, neutral in the middle. Okay, that's normal. In this configuration, I'm going to take the 2 batteries and put them in parallel, so all I get is 120. But my capacity is still the same. In other words, if this is 1 ounce or 1 VA, let's say it's 1 ounce and 1 ounce, that's 2 ounces. This is also 2 ounces. I could have shorter and fatter or taller and skinnier. It's the same capacity, except this would be 240 volts, this would be 120. Now, in 3-phase, we use 120 only. So it's a full capacity, but it's still 120. So, when we do this, and we have 120, we are, in this case, using the 2 bushings on the right, and we're saying, okay, that's the X in the center. The center one is going to be the common. See that? The common is going to our neutral. And then this one is for our red phase, this one is for our blue phase, and this one is our green phase. So that's our 3 phases. However, we have 120 from neutral to green, 120 from neutral to blue, 120 from neutral to red. Now the question is, what do we have line to line? Now this drawing tells you it's 208. Well, where does that 208 come from? If you take 120 line to ground, multiply it times the square root of 3, so you get your line to line, 120 times the square root of 3 is 208. So 208 is the standard value. That's what we use. So it's 208 3-phase. 208 between red and blue, between blue and green, and between red and green is 208. But any one of those phases to neutral is 120. We always deal with the square root of 3. So in a 3-phase bank like this, 208 120 is normal. It's standard. It's what is recommended, what is used with a grounded Y 4-wire system. On the primary is also a grounded Y 4-wire system on the secondary. Okay? There's other configurations, having a delta on the primary and a Y on the secondary. That leads into some distribution problems that we don't have time to get into right now. Stray current, stray voltages, blowing fuses unnecessarily. A lot of different issues that come up with a situation like that, where you have to float the neutral. There's all kinds of crazy things, and when you get into distribution, you'll learn all about that. So for right now, this is the standard, this is the normal, this is the norm, and that is a grounded Y, a YY 3-phase distribution transformer bank. Now let's talk about overhead fuses. Fuses are mounted in these fuse cutouts, which is basically an insulator that has a metal on this side and metal on this side and a fuse in the middle. The fuse is actually inside this tube. This tube is designed, because there's a spring on the bottom there, it's designed that when it's placed in its holder, current can flow from this connection through the fuse and out this connection. But if that fuse blows, inside there is a fuse wire that when it blows, it then allows the spring down here to operate and kick open the door, as long as there's no ice on it, you know, or it's it's stuck together from corrosion because of salt in the air, too much salt in the air or something. But it's supposed to blow open like this, and then a troubleman driving by can see that there's a blown fuse, okay? Fuse on a transformer here. The connection goes to the bottom, and then the phase is connected here, and then the lightning arrestor is connected up here. So when the fuse blows, the transformer clears. The arrestor is not protected by the fuse, notice that. So if the arrestor blows, then the feeder goes, or the fuse lateral to that feeder. So that's a fuse disconnect. The wire inside, you can change the rating of the fuse, whatever 3 amp, 40 amp, whatever it is. And then there's different types of 40 amp T's and K's, and all that is in coordination, which is a different course. Okay, let's talk about overhead to underground transitions. In this particular picture, you see the 3-phase, 4-wire overhead going into an underground riser. Okay, some companies call them dip poles, some call them riser poles. Okay, most of the time the power is flowing down, but not always. Because if you're going under an airport freeway or something, or airport runway or whatever, one side is going to be power coming out, and the other one's power going in. So, you know, if you disconnect, the disconnects up here, it doesn't mean that this isn't live or dead, because it could be backfed. So be careful about that. When you look close at that slide, you see that there's a fuse cutouts, 3 of them, 1 for each phase. The neutral wire is here. There are 3 lightning arrestors, 1, 2, and the third one over here. Then the wire from the fuse is going through the lightning arrestor to what's called a stress cone before it goes into the underground cable. The stress cone is a rubber device that allows the rubber to go over the jacket of the underground cable so any rain can go on the outside. It connects the center hot wire from the main overhead to the underground cable, and allows you to have a transition piece. So the skirts on the side here, just like on the insulators, allows there to be leakage current and minimize the leakage current for a overhead to underground transition. This metal bracket here has a ground wire connected to it, so there's a ground going down the side. So when they talk about bonded, they're usually referring to any of this metal being bonded to the ground wire going round. That's distribution. Now when we look at a distribution cable, underground cable, a couple things to note. First of all, there's 2 conductors. The primary conductor in the center, the hot conductor in the center. Then there's this conductive shield, which I'll explain in a second. Then you have the insulation itself, another conductive shield or semiconductive shield. The new conductor, this is the neutral, the concentric neutral, and then the jacketing over the concentric neutral. So the semiconductors act very similar to those grating rings on circuit breakers. It equalizes the electric field between the inner conductor and the outer conductor by equalizing the electric field around it in case there's any flaws or whatever with the conductors themselves. The insulation could be of any value. It could be for 12 kV, it could be for 69 kV, it could be 120 kV. You know, how much insulation you have between the two tells you how big the cable is and what voltage you apply, what have you. These concentric neutrals, there's a lot of them out in the world today that are not jacketed, and the copper neutral is disintegrating, it's disappearing from electrolysis in the earth. The copper is being eaten away, and it causes neutral voltage problems. And I mean, utilities stopped installing them a long time ago, but there's still some still out there. But anyway, that's a typical single-phase underground cable. Now, connecting those cables, you have elbows which plug on to transformers or switches, and you take the cable, the center of that cable, and you crimp it onto this crimp here, slide it, there's a threaded hole, you slide that all the way up, and you take this rod with the threads, and that goes in here and screws into that hole, and that makes your connection, and your cable goes into it there. So when you look at it, you got your cable coming in, cable goes up, there's a compression connector there, screwed in arc rod here, and this is a ring that you can measure to see if the line's energized or not, so you can confirm that it's de-energized before you work on it, and then the pulling eye up here to pull it off the connector. A splice says I'm going to have a cable on this side and this side. I'm going to route the concentric neutral up around the top. I'm going to crimp all that together over here. I'm going to crimp the two hot leads together in the center, and that forms a splice. Okay, I can take that and ground it. I can take the concentric and ground it. That's a splice. Failures in underground occur with splices and elbows, and sometimes the cable itself. You know, it's just what happens. In underground, you normally don't have reclosers automatically reclose. Why? There's, in overhead, you might have wind, you might have birds, you might have lightning that you don't have underground. If you have an underground failure, chances are there's something failed. Don't reclose, don't make it worse. If an underground failure occurs, trip and lock out. Okay? So that is underground cables and connectors. Now, when it comes to a three-phase pad mount transformer, again, we have the grounded Y input and a grounded Y output, 208, 120, just in a pad mount transformer. Okay? Now, I will like to note one thing here. This is 208 phase to phase. If you live in a condominium or you're in an apartment building and you have a washer and dryer or even a stove, the stove is going to be connected to 208, not 240. See, a residential house is basically 240, 120. Well, 240 applied to your stove or clothes dryer versus 208, the lower voltage means that the current flowing through your heating elements is a whole lot less, and therefore if the current's less, the I squared R heating is a whole lot less, and therefore it could take your clothes 20 minutes longer to dry, and that's normal. So if you live in an apartment or a condo that's fed by a three-phase pad mount transformer, your voltage is only 208, not 240, and your clothes are going to take longer to dry, and your stove might not say temperature degrees that are accurate. It might just say low, medium, and high, and whatever that is, because you're really running on a different voltage. Okay, so when it comes to underground pad mount transformers here, this is a three-phase transformer that allows you to have two sources, two three-phase sources, and here's the secondary over here, and that's 208, 120 three-phase. But this secondary, depending on how you turn that switch, could be fed from this source, both sources, or completely disconnected. Now here are the fuses, like fuse cutouts on overhead. These are bayonet fuses that are protecting this transformer on an underground pad mount. So if you open up those big doors, that's what you see. You got a high voltage side and a low voltage side. The concentric neutrals and all these cables are all tied together, grounded with a ground rod. And then you have your neutral, I think it's over here, is grounded. Here's the three phases and the neutral over on this side. So that's an underground pad mount transformer. Now, when you're putting underground elbows on, you know, the troubleman, the crew person is supposed to be using insulated hot stick tools. Plus, he's wearing rubber gloves. So even though theoretically you can actually touch a dead front connector, you're not supposed to, never should. You're supposed to always use the extra safety with the fiberglass rods, or shotgun in this case, and rubber gloves to do it safely. Now, in a live tank or a live front design like this, no bushings, it's hard connections, it's voltage exposed. You can't come even close to that, so you got to be very careful here. This is a switch that allows you to switch between feeders. You know, they look like this. You actually have control boxes on the sides. when you see underground distribution, you know, you can switch power sources around. Remember, it's radially fed, so somewhere you're going to have an open switch and other places closed, but you can close the open and open the close and switch load around depending if there's a bad cable you need to repair or what have you. So that basically shows you, but this is no elbows. This is all hard connections which could be, you know, dangerous if not careful. Okay, when it comes to service wires from these transformers to your homes, okay, for underground, you have two hots and a neutral, but the neutral has a jacket on it because it's going to be underground in a conduit, versus overhead, you don't have a jacket over the neutral conductor. So that's very typical of service entrance conductors going into a house. Now for overhead, you have what's called the weather head. You got the three conductors going into the weather head on the top, dropping down into the service panel where there's the meter. And in some cases, the circuit breakers are inside the house. Some cases, the circuit breakers are outside the house. Okay? In this case, for underground, you have the underground coming in. You got a meter socket going down and the service entrance equipment on the inside. So depending on the local National Electric Code and the local standards, you know, sometimes the distribution panel's inside, some are outside. You know, all my houses, they've always been outside, but when I travel around the country, they never heard of that. They always say they're always inside. What do you do in the snow? And, you know, it just kind of goes both ways, just for your information. Okay, so that's service entrance equipment. When it comes to metering, boy, there's a whole course on just metering. But to kind of keep high level and keep general about metering, some of the old meters were the electromechanical, and they were electromechanical because they had a coil of wire in there, so when the current flowing through your house created magnetic field, and then you had a magnet mounted inside here. When the magnetic field's repelled, this disc would turn based on how much current you're drawing and how much voltage you have applied. So the voltage and the current, when they both line up, they both can create magnetic fields. The voltage can apply to a coil, creating a magnetic field, and the current itself has a magnetic field. So when you put the two together, if the both norths are in line, you can actually have the disc turn. And when the disc is turning, then there's a 10-to-1 gear ratio. And these 10-to-1 gear ratios, you know, this would go clockwise, and because of the gearing, if this goes clockwise, this has to go counterclockwise, so the numbers are backwards. When this is going counterclockwise, this has to go clockwise, so then that number backwards. And the 10-to-1 gearing at least gave you an indication like an odometer in your car. So you'd read it 1 month, and you come back the next month, you see the change, and you mark down how much is used, and that's a kilowatt hours. Sometimes there's a scale factor, and you got to multiply that in, just like CTs and PTs do. Then the newer ones are solid state relays, or excuse me, meters. They give you more information. They can give you, you know, peak demand. They can give you current. They can tell you your operating timing. Now the smart meters are connected to communications that are two-way, so that you know, when you turn on and off a meter, you can do it remotely now through communication, which is pretty nice. I know I just moved recently, and I went to the new house, and I just called up the power company, and within an hour, you know, they switched my meter on. I just, you know, that was great. Didn't have to wait around. So the smart meters actually getting involved with the control of your appliances and giving you different rates for that. So depending on where you live and what your company, your power company is doing, provides you different options. When you get into a little larger metering scenarios, you have not only the energy, the kilowatt hours, but you also have demand. So there's a demand meter on the outside of this one. And what demand is, the difference between demand and energy, is energy we talked about, remember, kilowatt hours, energy, how many kilowatt hours did you use for the month? Well, demand says, what is the maximum demand you put on the power system for a 15-minute interval? If I had two big stoves going on, a friend of mine was making fishing poles, and they had two big electric stoves on. You know, if he ran them both at the same time, he would have a high demand. But when I told him, just run one stove, when it finishes, then turn the other one on, so your demand is half, your demand charge will be a lot less, your energy is going to be the same, but at least you saved on your demand charge. And same thing with lights at a Little League field. Once you turn those babies on, you are drawing your maximum power. And once you get hit with a demand charge, you might as well turn the lights on as often as you want because you just got hit with that. Now you're just counting on the energy. So when you want to time your billing cycle with when you start open house on Little League, you don't want to have like turn on the lights for open house and then the next day is your new meter reads. You just turned on the lights and paid a demand charge for nothing. I mean, demand charge is something that everybody with the bigger loads has a demand charge. They're paying for more generation to be added to the system because there's a coincidental demand. The whole system has a peak, and you're going to learn about this when you're operating power systems. There's a daily peak, a weekly peak, a monthly peak, a summer peak, a winter peak, an annual peak. That's the peak demand. Now, individual loads have their own demands. They're inconsistent. There is the when you have the total demand, and then when you have the independent kind of demand. And this is more of the independent, the demand charge on the meter. Okay, so that's metering. There are other types of metering going on now. With time of use and several other ones to coincidental and non-coincidental demands is what I was thinking of. But when you talk about other types of meters today, you can get into smart grid and time of use and so much energy management. If you're willing to have interruptible power, you get a different rate. There's so many different things going on now, but basically you're measuring energy, demand, and even in some cases power factor. The very large loads will be charged power factor metering. In that case, if you're running a poor power factor, you might be penalized for having the power company install capacitors to help reduce the current that you're sucking in because you have so many motors. But if you added capacitors on the load side of the meter and corrected the power factor, there wouldn't be a penalty. The power company wouldn't need to put the capacitors on. So you can trade off your power factor penalty for installing the cost for installing capacitors. So that's what happens on large systems. So when you're operating a power grid, you know, it all goes the same. You know, if you got load, well, how is the load figured out? How does it change? That's what this course is kind of explaining to you in a high level, some of the issues regarding load on a power system. Okay, let's get into wiring a little bit, residential metering and wiring. Power comes to the meter first, then goes to the panel, and there's a main breaker right here, and then little sub breakers going to the different rooms in the house and the kitchen and what have you. If you take that little metal panel off, you end up with a wiring configuration like this. There's the main breaker. You can see the breaker bar, and then you have sub breakers feeding the rest of the house. When you kind of break it down, you have the two hot legs, the 120, 120. This is shown here. One of the 120s is a solid line, the other one is dashed line. So what happens when you see the breakers lined up in the panel, they switch between which source they draw from. Okay? And the purpose of that is so that if you put two of them next to each other, you get 240. So you put a little plastic clip across the two, and that's a 240 source. Okay? Now you have the neutral comes over here and ties into the ground at the house. And the ground wires, usually the green wires, or in Romex, they're bare wires, also attach to the neutral bar. So if any of the wires were to short out, you would trip the breaker. If any of the hot wires were to short to a ground wire or the neutral, you'd trip the breakers. The newer panels actually have two buses, a neutral bus and a grounding bus, even though they're tied together, to separate the green or bare wires from the neutral. It's just a matter of different NEC standards. So just to keep that in mind. So that's basically how the panel is set up at a residential or small business load center. Now, if we take one circuit like the lighting circuit, taking one of the hot legs of the breaker through a switch, through the lights, and then the neutral side of the lights brought back as a neutral, and the green wire or the bare wire also goes back to ground, so that you turn on a switch and all the lights come on. You have 120 volts always from the switched on hot leg and the neutral. When you look at a receptacle, we have off the 120 breaker, you have a wire going up to the small slot on the receptacle. That's the hot wire. The neutral, which is the white wire, is connected up to the wide slot. Okay? And then the grounding bar or the grounding pin and the screw and all the metal that holds the socket in is all tied to the grounding. That's the way of doing it. These are polarized so that you don't plug them in backwards, just in case you have a light or a radio or a drill that has metal on it. If you plugged it in backwards, the metal could be the hot end. So you want that to always be the neutral end. Okay, that's a polarized plug. Some of the really old plugs, the pins were both the same size. So you could have a 50-50 chance whether you're going to get the neutral on the metal or the hot. So they made it so that you can't plug those in. So you get one of those green adapters. You can plug them in, but be careful. You can plug them in upside down, and what happens? It's all about electrical safety. So if this polarized and with the added grounding is very safe. And you add to that safety the ground fault circuit interrupters, the GFCI breakers. And what they're doing there is they're saying, okay, here's the source from the panel feeding the outlets. But the current that goes out the hot leg better be the same current coming back in on the neutral within 5 milliamps, or that breaker is going to trip. Because if it's more than 5 milliamps differential, it's assuming that that extra current is going through your body, through the wet floor or a metal connection, and it's going to take you out. So instead, it monitors, remember in a circuit, the current coming out of the source must equal the current coming into the source. So this is monitoring the amount of current going out the hot leg and coming in the neutral, and it better be the same within 5 milliamps or the breaker trips. Now, some of these breakers actually allow you to hook up more receptacles and operate off of that same protection scheme. So if you have one bathroom protected, it might be also protecting the kitchen and an outdoor outlet all off of one GFCI. So if a breaker trips and you go to your panel and you can't find the breaker that tripped on the panel, it could be the GFCI in a different room, because you're allowed to have extra receptacles off that same breaker. That's distribution. That's a little bit on electrical safety. When it comes to connecting up two 40-volt loads, again, you have two adjacent breakers so that you got both hots, 240, with a little plastic clip so that with one trips, they both trip. And you're feeding your dryer, your stove with 240. There's also a neutral brought in case you have a light in the stove or a clock in the stove, some things that don't run on 240, they run on 120. So you might have the neutral in there, so a hot leg, any hot leg, either hot leg to the neutral gives you 120. Then the grounding green attaches to the metal of the device or the appliance, so that if either one of the hot legs were to touch the metal, it would trip the breaker. So that's the grounding. That's 240 volt connections. Okay, so we talked about distribution, and now we're going to do a little summary of what we learned in distribution. Okay? First of all, we discussed distribution facilities, the primary feeders, remember radio, and talked a little bit about looped, transformer banks, customer services, service wires and transformers, how you, bad boy, alley cat, bad dog, those kind of things we talked about. Then we have, we compared overhead and underground distribution systems. We had the Y and the delta, and we had a single phase and three phase, how you configure and connect those up. We explained how the single phase and three phase transformer connections are made. Remember how we were talking about whether it's underground pad mount, you have loop through transformers. You have to go inside and change the taps on standard transformers if you want to use them for underground, those types of things. We described the differences between primary and secondary cables and hardware. The primary cables, we had the concentric neutrals, and then the secondary cables, we had the overhead and underground service wires, with the underground having a shield or insulation over the neutral, and the other one, the overhead didn't. Some of those and the breaker panels. We discussed the 120, 240 service entrance panels and how that is all connected up. And when we apply lessons learned here to distribution using the simulator, I'd like you to think in terms of when you look at the load and it has a little triangle and it calls it load, it's so many megawatts or something, think about what's making up that load. Think about its toasters, its motors, its lighting, its heating, all those kinds of things, and how that's always changing all the time. And what we're doing as controlling a power system is trying to match generation to all that changing load. And it changes night from day, from weekend to holiday. I mean, it's always changing. So when you think of the load and how it changes and how you can control generation and those types of things on a simulator, you're really actually operating a power system, without really causing any damage. Okay, so that concludes our module on distribution.